So from today, we will talk about the free radical copolymerization reactions. As you all know, we have already talked about the radical and ionic polymerization in Chapter 9 and Chapter 10. And those were chain growth polymerization reactions. We will further talk about the copolymerization reaction because we have already touched about the homopolymerization reactions. You remember that ionic polymerizations are much more complicated and complex than the radical polymerization reactions. So in the copolymerization reactions, we will just briefly talk about the free radical copolymerizations rather than ionic polymerizations. Of course, you can do the ionic polymerization reactions in making copolymers, but we will touch the copolymerization done by the free radicals. In this case, because we are dealing with at least 2 or 3 monomers in our system, we need to talk about the reactivity of the monomers. Okay? Reactivity of the monomers will influence what is the arrangements of your monomers in your polymer. Okay? Whether you can make the homopolymer, whether you can make the alternating copolymer, whether you can make the block copolymers or graft copolymers. So if you know the monomer reactivity ratio, then you can estimate what is the outcome of the reaction for your copolymer systems. And the monomer structure influences the kinetics of the radical polymerization reactions. So monomer reactivity, monomer structure are the most important keywords in this chapter 11. Okay? So we can talk about the free radical copolymerization reactions. In the radical copolymerization reactions, we have several types of copolymers, right? As you all know, we have alternating copolymer, where you have white stone and black stone are the 2 different monomeric units, A and B, or white and black. And you see those were in alternating each other. So whenever you have a white, next one should be a black, white, black, and white, and stuff like that. Whereas the random copolymer is the one that you have, there is no sequence. There is no order in the arrangements of white stone and black stones. So you have 3 white stone, 1 black stone, 2 white stone, 1 black stone, 4, stuff like that. And so you do not have any order. You do not have any the regular arrangements in white stone and black stones. So we call this as a random copolymer or ideal copolymer or random copolymers. Black copolymers are the one that you have, if you have 3 white stone, then you have another 3 black stone, and 3 white stone and 3 black stone, stuff like that. The number of these units, number of this white stone or black stone might be a little bit different, but whenever you have a block of white stone, next one will be the black block of the black stone, and so on. So. The block copolymer is different from random or alternating copolymer because you have at least the property of a white stone, in some case property of white stone, and the property of a black stone appear in both cases. Whereas this random copolymer or alternating copolymer might be different in terms of the total property of the copolymers, right? You do not see, in this case, you do not see property of white stone or black stone because it's too short to apart the property of a white stone and the property of a black stone of each case. Now, graft copolymer is the one that you have, at least you have white backbone, okay, white backbone, and the side chain might be the black or B monomeric units. Okay? This is something like a comb, okay, or graft, comb, the pit comb, or or the graft, so that this graft chain, this is something like a brush or the hair of your head. So your entropy of this, chain might be moving, or will be increased, so that you may have a different property of this graft copolymer versus the block copolymer. Okay? So in final composition, final property of this graft copolymer might be different from the rest of the copolymers. Okay? But however, in actual cases, the graft copolymer seems to be that there is no complete A or complete B as a comb, but you may contain a little bit of the other components, like white stone in the black pot, or black stone in the white pot. So in actual cases, there might be a little bit of deviation from the ideal copolymer system or ideal graft copolymer system, but in many cases, you have a comb, you have a brush, you have a hair in your own backbone of your copolymeric systems. Now, if you go back to the first slide, if you know the monomer reactivity ratio between the black stone and white stone, M1 and M2, A and B, okay, between the two monomeric units, if you know the monomer reactivity ratio, then I said you would be able to predict whether you can make the block copolymer, or whether you can make the graft copolymer, or whether you can make the random copolymers, right? So we will, next slide will show you the definition of the monomer reactivity ratio. Okay? Monomer reactivity ratio will be defined in the next slide, because we have to know about the how we can make this polymer. Okay? So in this case, we have a binary system, okay? Because we are talking about the two monomeric units. Now, I have written here in the kinetic equation, M1 dot and M2 dot and M1 and M2. So we have two monomers, M1 and M2, okay? White stone and black stone, or A and B, or M1 and M2. But we also have two growing radicals, M1 dot and M2 dot. So we have four species. Because we have four species, we have four equations here. Okay? M1 dot growing chain, M1 dot will have a chance to meet with the M1 or M2, so that the final the chain end will be M1 dot or M2 dot, depending upon which monomer that you meet. In this case, I have written here K11 or K12. You will immediately notice that the first number will be the growing chain, the type of the growing chain of your reactant. The second number will be the monomer type of your monomer, right? So K11 means M1 dot will meet M1. K12 means M1 dot will meet second monomer, M2. If you have a K22, then means that the monomer 2 radical, M2 dot will meet monomer 2. M21 means that you have a M2 dot should meet with M1 and making the M1 dot. So you have four chances to make the growing chain, okay, in the copolymerization reactions. K11, K12, K21, and K22 are the rate constant for each cases. Right? If the K11 is 1, okay, if K11 is larger than K12, then it means that there is a great probability of meeting the M1 dot meeting with M1 rather than M2. Okay, so the magnitude of this K11, magnitude of this K12 will tell you how fast the next chain will be, forming the next monomeric units. So those magnitude in the rate constants will tell you some information about next, the chain ends in this case. Now, we know that in this case, we have to assume always the steady state assumption. Okay? This is the sort of almighty solution in the chain cross polymerization reactions. Okay? We know that the dm1 dot over dt, meaning that the disappearance of m1 dot, or the rate of disappearance of the m2 dot, it will be expressed as minus dm1 dot over dt. Okay? dt, d over dt is the rate, okay? Rate derivative of m1 dot over time will be the rate of disappearance of m1 dot is equal to the rate of disappearance of m2 dot is equal to 0 when you have the chain transfer and termination, okay? Compared with the propagation. Okay? And that's what we can say that the steady state assumption. And in this case, although it's not 0, if you think about the first case, the second equation and the third equation is equal to 0 in this case, and K12 times M1 dot over M2 is equal to K21 dot M2 dot times M1, and if you rearrange this equation, you can come up with the first equation here, whereas M1 dot over M2 dot ratio is equal to the known rate constant K21 over K12 times M1 over M2. Now M1 over M2 is the initial monomer concentration, whereas M1 dot, concentration of a growing chain, M1, and concentration over M2 dot is not, as you already know, it's not possible to account in your rate equation. So we would like to eliminate M1 over M2 dot as known constants and known concentration, okay, here in this case. So therefore, we will use this equation number 1 later in our, the Copolymer equation, derivation of Copolymer equation. So in this slide, we need to know we have 4 cases, although because we are dealing with the 2 monomers and 2 growing radicals, and we defined K11, K12, K21, and K22. Okay? And in the steady state assumption, we need to know that the rate of disappearance of M1 dot and rate of disappearance of M2 dot will be the same. And in this case, equation number 2 and equation number 3 will be exactly the same, so that we can derive the equation number 1 here, which means that the ratio of the radical concentration during the reaction, ratio of the radical concentration during the polymerization can be expressed as known constants and known concentrations. So, and also we can derive that the disappearance of M1, okay, rate of disappearance of M1, rate of disappearance of M2 can be expressed as the equation number 1 and 3, because rate of disappearance of M1 is only the first equation and the third equation. Rate of disappearance of M2 will be determined by the second equation and the fourth equations. So minus dm1 over dt is equal to first one and the third one, minus dm2 over dt is equal to second equation and the fourth equation. All right? And if we rearrange this equation, dm1 over dm2, which means that if you put this equation divided by this equation, you can rearrange this the second equation here. Okay? Second equation. Now in the second equation, we have M1 and M2, K11, K12, K21, and K2. Excuse me, K. This is K21, and this I think this is K22. So there is a mistake here. Sorry. This is K22, and M1 dot and M2 dot. Okay, M1 dot and M2 dot. Now, M1 dot and M2 dot should be eliminated in our copolymerization because we always have done that, right? So in the final equation, we need to derive this equation. Now, if we combine first equation and the second equation, first equation and the second equation, then we can come up with the some other equations here. From the first equation, second equation, we can say that dm1 over dm2 is equal to 1 plus r1, whereas r1 can be defined as k11 over k12, and r2 will be the k22 over k21. Okay, if we define this, the ratio of the reactivity, ratio of the rate constants, then I think we can come up with this simplified equation here from this equation. This is R1 and R2. R1 and R2 will be defined as monomer reactivity ratio. Right? Monomer reactivity ratio. Okay? I will explain to you what is this, the meaning of this. Okay. Anyway, now dm1 over dm2, derivative of composition or concentration, has some meaning, although it could be expressed as mathematical ways. But in our chemical engineer's viewpoint, dm1 over dm2 will be the instantaneous ratio of the monomeric units in the copolymer system. Okay. M1 over M2 M1 is the monomer concentration of the first monomer, M1, and M2 will be the concentration of monomer 2 at any point or at initial point, at initials. dm1 means that monomeric units that you put in the reactor, right? But finally, after some time, you could make the polymer or copolymer systems, but you do not know whether this M1 in the initial reaction will be completely come up with the copolymer systems, right? So dm1 could be the copolymer monomeric units in the copolymer systems. Monomeric units in the copolymer system, dm1 or dm2, may not be the same as initial concentration of monomeric units, M1 and M2, that you put it in the reactor, right? So dm1 over dm2 is the monomeric units in the copolymer systems, whereas M1 over M2 is the monomeric units in the reaction, okay? At the beginning of your reactions. At the beginning of reaction, this is the monomer concentration ratio. This is the final monomeric units ratio in your copolymer systems. Later on, we will define the small f1 and large f1, which might be related with the M1 over M2 and dm1 over dm2 later on. But anyway, we can say that dm1 over dm2 will be the copolymer equation, meaning that when you would like to know about the monomer concentration, monomer units in the copolymers, then you need to know what is the reactivity ratio of each component, R1 and R2, and monomer concentration at the beginning of your reactions, M1 over M2. So if you know M1 over M2 and R1 and R2, you will know dm1 over dm2, which means that the monomeric units in the copolymer systems. That's why I told you at the beginning that if you know the reactivity ratio, monomer reactivity ratio, R1 and R2, you will be able to predict whether you could obtain these monomer units could be rearranged into block copolymer, or could be rearranged into a random copolymer or ideal copolymer, stuff like that. And so this is very important equation, whether you will, so we call this as a copolymer equations. Copolymer equations. Okay. Copolymer equations can be reduced from monomer concentrations of each component, M1, M2, and R1 and R2, the monomer reactivity ratios. Now, monomer reactivity ratio is defined as K1 monomer over K12. R2 is equal to K22 over K21. If R1 is equal to 0, okay, if R1 is equal to 0, that means whether you have 0 K11 or whether you have infinite K12, right? So if this is equal to 0, that means that you have K11 might be 0 or K12 might be infinite. Which means if you have a growing radical, the first one is a growing radical, right? Species of the growing radical. If you have M1 dot meeting with M1 or meeting with M2, which is defined as K11, this is defined as K12, right? Right? Now, if R1 will be 0, then means that K11 will be equal to 0, right? K12 will be infinite. This means that if there is any M1 dot formed during the reaction, there is no chance to meet with M1, but there is a great chance to have a M1 dot meeting with M2. And this is preferable. So whenever you have a M1 dot, you should meet with M2 rather than M1. And if R2 is equal to 0, right, then K22 will become 0 or K21 will be infinite. This means that whenever you have an M2 dot, there is no chance to meet with M2, but there is a great chance to meet with M1 to become M1 dot, right? So if R1 will become 0 and R2 becomes 0, right? If you have a much lower, very close to 0, then you always have to have a M1 dot meeting with M2 to form M2 dot. And when you have M2 dot, you only have to meet with M1 rather than M2, so that you will have a M1 dot later on in this case. So in this condition, when R1 and R2 is close to 0, your final copolymer composition will be something like this, which means which copolymer? Alternating copolymer. Alternating copolymer can be formed by knowing what is this R1 and what is this R2. if this R1 and R2 is close to 0, then there is a great chance to form the alternating copolymers. And in this way, we can predict the copolymers. But if it is not 0, but close to 0, we call this value as alternating tendency. Okay? When R1 and R2 is not completely 0, R1 and R2 might be 0.1, 0.1, 0.2, or close to 0, then we can say that we have an alternating tendency. Alternating tendency. Although it's not completely alternating, you may have an alternating tendency. M1, M2, M1, M1, and M2, stuff like that. So we have an alternating tendency in this case. Now, in the second case, when you have a 1, R and R2 is equal to 1. When R1 and R2 is equal to 1, K11 chance to meet with the K11 is equal to K12, right? K22 will be equal to K21. This means that whenever you have M1 dot, there is an equal chance to meet with M1 and M2, right? In this case, M2 dot can meet with M2 or M1. There's equal chance. So in the final composition, you have a M1. If you have M1 growing chain, there is a chance to form a M1 or M2 right? What is this copolymer called? This is what we have said, the random copolymer or ideal copolymers, right? The chances to form, to meet with M1 and M2 is equal, so that the final copolymer composition might be random, right? Because we have an equal chance to form the copolymer systems. So when R1 and R2 is close to 1 or equal, then random copolymers. Finally, when we have R1 greater than 1, R2 greater than 1, right? In this case, K11 is much greater than K12. K22 is much greater than K21, right? So you have a great chance. I do not want it to reiterate, but whenever you have M1 dot, there is a chance to meet with M1 rather than M2. Okay? Whenever you have a M2 dot, the next monomeric units will be M2 rather than M1. Of course, you can have in some cases, you can meet with M1 from M2 dot, but whenever you meet with M1 dot, meet with M1 and to become M1 dot, there's M1 dot formed again. So final copolymer will be block copolymers. Right? So by knowing R1 and R2, you will be able to predict the composition of your copolymers. By knowing R1 and R2, then you can predict the exact composition in your copolymer systems from the monomer concentrations that you put it in the initial the reactor, and R1 and R2. Okay, So we define R, small r, right? Small r, then I have elaborated a little bit about the flavors of, what is the meaning of R, or how does the R affect your final compositions. And we need to know about the small f1 and large f1. I've written down small f1 and large f1. Small f1 is the monomer feed ratio. And the large f1 is the polymer composition, the composition of the monomer 1 unit, monomer 1, in your copolymer systems. Okay, so mole fraction of the monomer 1 in copolymer will be defined as large F1, whereas the small F1 is the monomer composition in your monomer mole fraction in your final the feed. Okay, is a small F1, whereas F1 plus F2 will be 1. Okay, if you have a mole fraction of monomer 1 plus mole fraction of monomer 2 is equal to 1, right? So small f1 plus small f2 will be 1. Large f1 plus large f2 will be equal to 1. So let's define the meaning of R and the meaning of this small f1 and large f1 again. So R1 is the characterization of the reactivity of radical 1 over the two monomers 1 and 2. Okay? Radical 1, M1 dot, meeting with the M1 or M2 is defined as a small r1. If small r1 is greater than 1, then means K11 is greater than K12. So you have a great chance to form a 1111 rather than 12, right? If R1 is equal to 0, then means that K11 will be equal to 0 or K12 is infinite. So whenever you have the first radical M1, then next monomer will be the second one. Okay, so we can come up with this summary in the next slides, but let's define small f1 and large f1. Small f1 again is the mole fraction of the monomer in the feed in the initial cases, and the large f1 or large f2 is the mole fraction of the monomers in your polymer, okay, copolymer systems. Therefore, the small f1 is equal to 1 minus f2, right? Mole fraction of the first monomer and mole fraction of the second monomer is equal to 1, or 1 minus f2 is defined as monomer concentration of 1, because this is 1 here in the subscript, and the monomer concentration of 1 plus monomer concentration 2 will be defined as the denominator. Okay? So small f1 is the mole fraction of the monomer in the feed, in the initial feed, and large F1 is the copolymer system. We are talking about the copolymer systems. So dm1 over dm1 plus dm2 is defined as large F1. Large F2, of course, will be dm2 divided by dm1 over dm2, right? So if we rewrite the monomeric units in the copolymer system, mole fraction of the monomer 1 in the copolymer system, large F1, can be rewritten in terms of R1, R2, and F1 and F2. F1 and F2. F1 and F2 is the mole fraction in the feed, because we know from your copolymer system, we have derived here in this case, right? This is not large F1 and large F2, but you can rearrange the Copolymer equation to make large F1 as a function of R1 and R2 and small f1 and small f2. So please do by yourself to derive this final equation here, right? This is your task. And please, this is the second or third homework to submit it to next Wednesday. So please derive this copolymer equation in different form, large F1, because this will be very much helpful later on to get the composition in your copolymers from RnR2 and the feed mole fraction. So from equations 3 and 4 and 2, the copolymer equation, we can derive this the copolymer equation in different form. Now we need to talk about the ideal copolymerizations. Ideal copolymerizations already been talked about here, where RnR2 is equal to 1 cases, right? Or RnR2 is equal to 1, or Rn times Rn times R2 might be equal to 1, is the case where we have ideal copolymerization reactions or random copolymerization reactions. So you have a random composition in your final copolymer will be defined as ideal copolymerization or random copolymerizations. Now, if you remember, this is the copolymer equation in a different form of copolymer equation. So dm1 over dm2 is m1 over m2 times R1 times m1 plus m2 divided by m1 plus R2 times m2. Okay. If you go back to your copolymer equation, equation number 2, copolymer equation, then this is the different form of copolymer equations. Remember that you have a dot here. Okay, dm1 over dm2 is equal to m1 over m2, which is different from f1 and large F1. But anyway, you can rewrite this equation. Now, and R1 times R2 is equal to 1 could be the case where we have ideal copolymer equations. So you can rewrite when R1 R2 is equal to 1, R2 will be 1 over R1. So when you replace this R2 into here, you can come up with this equation, and you can cancel this out because numerator and denominator will be the same. So when R1 R2 is equal to 1, dm1 over dm2 will be R1 times m1 over R2, m1 over m2. So if you know the monomer reactivity ratio of the first component, then you will be able to predict dm1 over dm2 by knowing the m1 over m2. And large F1, equation number 5, can be rearranged into a small, the very simplified equation here, large F1 here. So most the ionic, most R1 R2 is equal to 1. In this case, K11 over K12 is equal to K21 over K22. And this is very simplified ideal polymerization reactions. When R1 and R2 is equal to 1, where R1 times R2 is equal to 1 here, we can have random copolymers, of course, okay, as we have already described here in this case. Any questions so far? Okay. Now, when when you have ideal copolymers where R1 and R2 might be equal to 1, okay, or R1 times R2 is equal to 1, right? In this case, R1 might be 1.5, R2 might be, let's say, 0.1 or 0.2, so that let's say that R1 might be 1.2, 1.1, and R2 might be 0.1. I'm sorry. In order to make the 0.99, for example, 0.99, then to make the equal to 1, then you have a larger R1 and smaller R2, or larger R2 and smaller R1, those cases. When we have ideal copolymers, usually the small F1 monomer mole fraction could be plotted with the monomer mole fraction in the copolymer systems, okay? Just like a distillation curve in your case, in your chemical engineering case. And you can form azeotropic line here, where a small F1 is equal to large F1. Okay? You can plot it with the same lines here, and this is what we call the ideal cases. You can have a larger one and smaller one curve, depending upon what is the value of a small R1 and a small R2. Right? If you have a smaller R1 here in this case, your plot will always follow this line here, below this azeotropic line, where if R1 is greater than 1, it will always follow above this ideal copolymerization lines. Okay? And that's the very typical cases here in this case. So when you have a more reactive, the monomer, in this case R1, and in this case the monomer 2, then the more reactive monomer will be much more the larger in portion in your copolymer systems rather than the other second components. So this curve will tell you about what is the composition in the final cases. Now, for example, if you have alternating copolymer systems, usually I told you that R1 and R2 might be equal to 0, right? But if R1 and R2 is equal to 0, when R1 is equal to 0, then it will finally come up with the 0.5 point here, okay? Small F1, although if you increase a small F1 to 100%, your final copolymer system will come up with 50% of the monomer 1 in your copolymer systems. And the rest of them will be the second monomer. Okay? That's what they call the alternating copolymer systems. Because if you think about the alternating copolymers, you have M1 and M2 and M1 and M2, and the final composition might be 50% of your M1, the 50% of your M2, regardless of your reactivities. Because your reactivity, R1 and R2, is very low, very small, right? So that although you increase your final the composition, you can come up with the large F1 is equal to 0.5, and the rest of the monomer will be lost. Will become not the polymer, but will be lost. So this crossover point will be defined as azeotropic line. Okay, azeotropic line, just like the chemical engineering, distillation curve. And again, when R1 and R2 is equal to 0, or approaching to 0, then we say that this is the case where we have an alternating tendency. And if the R1 and R2 is equal to 0, we say that this is the perfect alternation. Okay? Here, in this case, when we have a perfect alternation, because R1 and R2 is equal to 0, dm1 over dm2 is equal to 1, or large F1 is 0.5, because if you go back to your Copolymer equations, now R1 and R2 is equal to 0, so you can cancel this out, R1 here, and F1, F2 will be cancelled out. So the large F1 is equal to 0.5. Okay, you can predict that 0.5 in your copolymer systems from this Copolymer equation as well. Or if you go back to your original Copolymer equation number 2 here, then R1 and R2 will be cancelled out because it's 0, and dm1 over dm2 should be 1. Okay, so dm1 is equal to dm2, meaning that monomer units m1 in the copolymer system is equal to monomer units, number of monomer units m2 in the copolymer systems, right? dm over dm2 is equal to 1 means dm1 is equal to dm2. So if you go back to your original Copolymer equations, you can come up with the same. So in the case where I think we need to think about the final composition of M1 and M2 in large F1 and large F2. And these points, when we have a small F1 is equal to large F1, is called the edgeotropic line. And edgeotropic line is only formed when you have perfect alternating cases. Or when you have R1 and R2, the greater than 1, we have a block tendency. But if it's infinite, R1 is equal to is infinite, R2 is infinite, then we only have a homopolymers. Okay? But if you have a reasonably good and large R1 and R2, we call that as the block tendency or block copolymer compositions. So meaning of the crossover point is that large F1 is equal to small F1, okay? Where we have an edgeotropic line. And at these crossover points, the copolymer and the feed compositions are the same, and therefore the copolymerization occurs without any changes in the feed compositions. And this is what we call the edgeotropic copolymerizations, where large F1 is equal to small F1. Okay? When you have perfect linear compositions, that's called the edgeotropic copolymerizations. And conditions for this edgeotropic composition is that because we have a large F1 is equal to small F1, okay, and dm1 over dm2 is equal to m1 over m2, okay? Or m1 over m2 is equal to R2 minus 1 over R1 minus 1. Okay? I think you can redefine this large F1 and small F1 so that you can derive this equation. Okay? And therefore, because we know that large F1 is equal to small F1, and we can redefine M1 over M2 or dm1 over dm2 here in this case. What about the alternating copolymers? Okay? Alternating copolymers are the ones that dm1 over dm2 copolymer equation can be redefined that R1 and R2, the dot or R1 times R2 is equal to 1, right? Or R1 and R2 could be 1, so that you can derive the equation where written in the second case, and M1 over M2 is equal to, here in this case, and because F1 is defined as M1 over M1 divided by M1 plus M2, so if you can rearrange this equation, you can come up with large F1, small F1 is equal to 1 minus R2 divided by 2 minus R1 minus R2. Okay? Therefore, depending upon what kind of copolymers that you obtain, whether you obtain the alternating copolymer, tropic copolymer, or ideal copolymer or random copolymer, then you have different R1 and R2 values, so that the copolymerification might be modified to your needs, okay, in this case. Okay, now in many of the textbook or many of the textbook on the polymer chemistry, you see these type of the graphs. Okay, I told you that the intersection line between the small f1 and large f1 here, this is the azeotropic line, right, where the R1 is equal to 0. When R1 is greater than 1, then you always have a upper bound, okay, the curves above this R1. Where R1 is less than 1, then you always have the curve below this, the azeotropic lines. Here in this case is the same. When R1 is equal to 2, then you have the upper bound. If R1 is equal to 0, then means that you have alternating tendency, so that if you plot the F1, small f1 and large f1, it will approach to the 0.5 in your final large f2. Right? Now, we have one more thing that I have to emphasize here. If you look at this arrow, the arrow is called drift. It's called the drift, and this drift is coming down when you have above this azeotropic line, or if it's below your azeotropic line, it comes up. Okay, arrow is coming up always, or arrow is coming up, arrow is coming down when it's above this azeotropic line. Okay. So if you take a look at the R1 greater than R2, if R1 is greater than R2, R1 is much larger than 1, or R2 will be much smaller than 1. Okay? And in this case, there is a tendency for the homopolymerization of the two monomers. And if R1 times R2 is equal to 1, then we have ideal copolymerization or random copolymerizations. If R2 is equal to 0.5 and R1 is equal to 0, then R1 is equal to 0 means that we have alternating tendency. If R2 is much smaller than 1, we also have alternating tendency as well. But since R2 is not equal to 0, but it's about 0.5, you may have a little bit of the second component in your copolymer systems more, but because R2 is approaching to 0, I think we have alternating copolymer in many of these cases. If R1 and R2 is equal to 1, then means that R1 might be 1, or R2 might be 1, or R1 might be 2, and R2 might be 0.5. Okay? If R2 is equal to 2, then we have this curve, meaning that when you add 50% of your monomer 1 in your feed, then you come up with the larger percent, like 80% of your copolymer when you feed about the 50-50 of your the monomer composition, monomer mole fractions. So depending upon depending upon the monomer mole fraction in the feed and the magnitude of R1 and R2, at which point, if you terminate your polymerization reactions, you will be able to find the composition in your final copolymers. Okay? So R1 and R2 is important, of course, but R1 and R2 might not be exactly the same as 0 or 1 or the infinite, but it could be relatively small and larger in some cases, and also the small f1 and m1 over m2 will determine your final composition of the copolymer systems. When the R1 is equal to 0.5 and R2 is equal to 0.5, then you have crossing this point, okay, and therefore it will reach to alternating tendency, and if the R1 is equal to 1 and R2 is equal to 0.5, you always have R1 greater than 1, so that greater than 1, R1 is equal to 1 or greater than 1, so you do not have any azeotrope in this case. If R1 and R2 is all larger than 1, then you have a block copolymer systems and following this line, as you can see here in this case. So in summary, when you have a drift, approaching to a 0.5, then you have a block tendency. When your drift is spreading out, then you can come up with alternating copolymer systems. Alternating copolymer systems. Now, so far, I think we have talked about the copolymerication, right? Copolymerizations in equation number 2, assuming that we have a steady state. We assume the steady state to eliminate the concentration of your radicals, right? Concentration of radical could be eliminated to know about the copolymer composition in terms of the known constants and known field compositions. Now, from now on, this homework is the homework that is related with the different cases. Now, we define the monomer reactivity ratio, small r1 and small r2, by eliminating the radical concentrations, right, in the growing chain. What if we define the radical, instead of a monomer reactivity ratio, what if we defined radical reactivity ratio by eliminating monomer concentration and remaining the copolymerization in terms of the radical concentrations? Okay, this is the opposite way of what we have already defined. Now, this is not realistic, okay, but let's define the radical reactivity ratio instead of monomer reactivity ratios. Okay, please do the homework. Please obtain the homework by assuming that you define the steady state assumption for monomer concentration rather than radical concentrations, so that you substitute this original composition equations with this active center rather than monomer concentrations. And then you need to define the new reactivity ratio called the radical reactivity ratio rather than monomer reactivity ratio. Okay? So define large R1, large L2 rather than small R1 and small R2. Okay? and then you can come with the copolymerization in terms of radical concentration rather than monomer concentrations. I think you can do, okay, because by solving this equation, solving this problem, you can reiterate the already known equations that we have studied so far. Okay, from slide 1 to slide 12, you have to study about the previous slides so that you can come up with the different equations. So I have two homeworks today. So I have two homeworks. So first one is you can derive this large F1 in terms of R1 and R2 and small F1. The second one is you can derive the radical reactivity ratio in terms of radical concentrations rather than monomer concentrations. I hope you can derive this equation by Friday, if it's possible. Excuse me, the day after tomorrow. Too much for you? Next Wednesday then, okay, next Wednesday.